So let's start talking about shear. We'll do shear and deflection examples from the problem we previously did just for flexure. And so starting with shear, it's in section 3.4 of the NDS of your code. Horizontal shear is what we're calling, just to differentiate. We're going to look at shear. This is basically the traditional shear that you're used to looking at. We know capital V is what we've traditionally used for shear. That's a shear force due to the loads. And this little f sub V is actually our shear stress. And so remember, we're doing stress now, so you got to go back to your mechanics class. I learned it in mechanics is BQ over IT. We're going to use B here because that's what we've been using for thickness. It's just a different term for thickness, and you may have learned it this way anyway. So, got to remember that equation and remember what terms those are. So, this is shear stress, and the little f means it's on the demand side. Q is static moment of inertia. I think some places call it statical. I always called it static moment of inertia. And that is BD squared over 8 for a rectangular member, which is primarily what we're dealing with right now. We can look it up as we need to for other types of members. And I is the same as we've been using. It's the same I, B, D cubed over 12 for a rectangle cross section. And so our F sub V, or our shear stress, is going to be 3B over 2BD. All right, so we go ahead and simplify based on Q also is related to B and D, so we can get a final equation that is essentially 1.5 V, so 150% of the shear over the cross-sectional area, or 1.5 B over A. All right, so that simplifies down. In mechanics, you had to deal with this Q and stuff because you were looking at all different kinds of cross sections. We're primarily going to be looking at rectangular members for a while here. Okay, so that's the equation you want to use for shear stress. All right, let me, move forward here. Flexural limit state, just like always. So the shear stress, demand, less than the adjusted allowable. All right, but now we're talking about shear stress. So same deal, different type of stress that we've been doing. Same thing, large S on the allowable side is prime because you're going to have adjustment factors just like before. Let me go back just a second, make sure that I forgot to hit these two things. So in NDS 3.4.3.1, it says for uniformly distributed load, you can consider the max shear at D away from the face of support. Sounds suspiciously like concrete. Just remember D in concrete is to the bar and this D is the height. Okay, so that's helpful. That means, let's say we have a uniform simply supported beam. Just like in concrete design, I don't have to design for this peak. I can design for the place where I out the distance from the support, right? So that makes a lot of sense if you think about what's going on. It's the same with concrete. What's going on in the bearing region, you've got that compressive force. You also, if you're looking at the center line to center line versus clear, this is actually over support. But the code allows us to go out D away from the face of support. You need to do that when you're doing your design because you're going to be super overly conservative if you look at this at the top. Typical unnotched beams, shear is not the thing that's probably going to control in wood. So you want to look at the maximum shear along the beam length. Typically, this is going to be, if you have a typical case, the near the ends, D from the ends is going to be your max. Remember, you have to do pattern loading and things like that depending on what the member is. If the member has basically primarily dead loads that are all across the beam, the shear diagram basically looks like this, and you're going to have your peak over as close to the support as the code makes you go. Notch beams we talked about a little bit in the first part of this chapter, and we'll do an example to check the notch pieces when we do the shear part of the example we did for bending. Excuse me. Okay, so we go back to table 4.3.1 to get our factors. So go into your specification in chapter 4, or your code in chapter 4, and on page 29 is 4.3.1, and it's the same idea as before, except for with shear, we actually only have to do 4. So we do CD, CM, CT, and CI. So F sub V prime is F sub V times CD, CM, CT, and CI. All right. Notched beams. So like I said, we'll do an example here. When I'm talking about D sub n, that's the depth from the top of the beam to the bottom at the notch section. So not the cutout piece, but the depth of the part of the beam that has a notch in it. So in the NDS, we don't look at stresses to check the notch. We actually look at the force. So we compare the maximum shear, V. Okay, we're going to look at the maximum shear on the beam, the design shear for rectangular beams notched on the tension side at the support. Right, so if this is a rectangular or as a simply supported beam, right, it goes like this. So the tension side's on the bottom. Right, so tension side, which is most likely if you're notching the beam to get a certain clearance here or to tie in at a certain level. So for rectangular beams notched on the tension side, V sub R, so similar to what we've been doing, but V sub R is calculated using the adjusted shear stress, the area of the notch portion, so just this area here, stress concentration factor, and the depth of the member remaining at the notch. Okay, so we'll go through this and go take a look at 3.4.3.2 so you can see what this looks like in the code section. Beams with other shapes or types of notches, there's different concentration factors, and you can follow the NDS for that, but this is for a rectangular beam. All right. So I'm just going to do a short overview here, and then we'll jump into the example to deal with how this works. Okay, deflection. So obviously you're going to do the bending. It's similar to other stuff we've done. You do the bending first. You are not likely to, that's likely to control. You're going to do that bending. You're going to do the shear to make sure it still works, just like we do in concrete. If you have a notch beam, you could check that first if you think that's going to be an issue. Beam deflection, again, this is a service requirement. This is not a safety requirement. Now, it doesn't mean it's not important, because if you have too much deflection, you can have anything from the elements that are sitting on the beams, like the drywall or flooring or whatever, can have damage. You could have a floor that's a little bouncy, which is not something people like, etc. But it's not a safety concern in this case. So what do? You compare the calculated deflection to deflection limits like we always have done. The deflection of wood beams uses the normal equations. For instance, for a uniformly loaded, simply supported beam, that's good old delta equals 5W L to the 4th over 3 84 EI. If you don't remember that one at this point, you should probably commit it to memory. That's the one deflection equation that's helpful to have off the top of your head. Obviously, W is the uniform load, L is span, and always watch units on these things because there's a lot of units in here, a lot of inches and feet mixed up, and you've got the EI term. The difference is this is going to be E prime. Okay, so we'll talk about that. Everything in wood, we have to have the prime to adjust it for the given situation. All right. Oops, did I somehow added in the wrong place? Okay, beam deflection. As I said, it's a serviceability limit state. The recommendations, when we look at deflection limits, this is basically going to be a combination of the loading piece in ASCE 7, which has this statement, shall be designed to have adequate stiffness to limit deflections, deformations that adversely affect the intended use and performance. It's a little generic, so what we typically will do in all these different types of things is we go look at deflection limits based on deflection tables. So like in ACI, you go to that part of the ACI code for concrete and you look at the deflection limit tables. And in that particular case, they have limits based on type of use, which is similar to what we're going to see here. The International Building Codes, just go to the governing code, has a table with deflection limits, and AITC is actually the American Institute of Timber Construction, and that is glulam. They have some glulam tables. So if you want to go look, they have these tables for the glulams. We're not doing glulams right now, but the tables are in plib.org/AITC. So this is the Pacific, shoot, where did I see that? Pacific Lumber Inspection Bureau is PLIB, and all these guys merge together. So PLIB continues to keep the information that was in the AITC for glulamps. And so they've got, go to that web page, they've got standards, some quick tech note links, beam capacity tables, and things like that. Okay, so they also have some tables. You can go look at them. For our purposes and IBC, when you need these tables, I'll give them to you. All right, deflection limits. So this is that 1604.3. Similar to what you're used to seeing in the concrete class, it depends on kind of what you're supporting, how strict the tolerance level is. Here they're talking about your live load deflection, snow or wind, dead plus live combinations. And so you can see the deflection limits here. Of course, service loads. And they're the typical L over 240, L over 360, L over, you'll see the 400s in the next one. If it's not supporting really anything, then it's got a less stringent rule. These are the ones from AITC that include all lumber pieces, and so roof beams, you can see in here we get up to the 400s, railway bridges. This is a big generic one. And increased floor stiffness. So where I need increased floor stiffness, now I'm up into the 480s. Sorry, got allergies badly today. Up in the 480s. Okay, so you'll know what deflection limit applies by the tables I give you along with, or I'll just give you the deflection limit. All right, so we are ready to start on that same example we did before, but we're going to add in here to now go ahead and do shear and deflection and show a notch detail that we're going to have to deal with. All right, I'm going to stop this one.